Good morning. Well, this is Mr. Baker. Miss Harris and I and all the other math teachers are at a training, so you get to watch this wonderful video. I know you guys want to hear your daily joke, so I had one about construction, but I'm still working on that one. Ha ha. Oh, well, there's this other one I know about paper, but it's terrible. Okay, okay. I do have a joke about the ceiling. It's probably over your head. Hopefully your eyes are all rolling now. So today we're going to looking at linear inequalities. We've been working with lots of linear equation stuff today, so throwing in that inequality piece here. I'll be looking at how we use interval notation when we're solving an inequality to represent the solutions. First off, we're going to look at looking at a graph, how to represent the solutions to a graph using interval notation. So do make sure that you want to use that particular notation. It's not the set builder notation. You want to use that interval notation. So I will probably start off looking at it as an inequality and then transfer it into in the interval notation. So kind of going from one thing you should be a little bit more familiar with to another thing that you are still working on. So, all right, so we have these two lines here. And we have a few questions over here on the right that we want to answer about what they will look like. So where does f of x equal g of x? And so what we're looking at here is where does this line equal this line? And so remember, one of the things you got to realize is that when we say f of x, that's the same thing as saying y. So where's the y value of f equal to the y value of g? Okay, and so our solution here is going to be that x value. What's the x value when y of f is the same as y of g? And so what we're looking at, that is that intersection point. Okay, so there's our solution, or there's our x value when the two y values are the same. And so far as the interval notation, well, there's only one x value that has the same y value for both, and that would be 1. So, and since it's at 1, it's going to get a bracket. So if x equals 1, then the two y values are the same. That's what that's saying. This next one is saying, where is the y value of f greater than or equal to the y value of g? So when I think about this, what I'm thinking is like, since our y is our vertical component of the line, so where is the line f higher or equal to line g? And so what I'm seeing with that is here. This is where line f is higher than line g, or equal to in that intersection point. So again, what that means when I read this, where's the y component of f higher or equal to the y component of g? Okay, so where's the line f higher than line g? If that's confusing to you, sometimes we can think of it more in context, and it might be, this is a pretty abstract idea. We're just looking at a graph. Nothing really means anything. If we could put some context to the problem, then sometimes it's easier to understand. So I'm going to flip over to a different graph. You guys don't need to draw this one or anything. I just want to maybe explain it to you in a different way, see if it makes more sense. So that's what we're up to here. So when is that line f higher than or equal to line g? Well, it starts, or it's equal to at 1. Right, we're going to roll at the x values here, and it keeps being higher than g all the way forever. All right, it's never going to dip back down because it's a line. So it starts at 1, so that's going to be a bracket since it's the equal to, and then it's going to keep going forever, being higher than g. So that's how that works. The next thing it asks us is when is f, so when is the y value of f less than 0? So when is the graph of f below 0? And so what I'm seeing here is, well, here's where it is 0. So when is it below 0? That's all this time. Okay. So I'm looking at this space here. Oops. All right, so when is that happening? All right, so as we think about the domain, right, we always want to start on that left-hand side of the graph, and that, it's going to keep going left forever, so there'd be an infinity. But it's negative infinity since it's going left. And then when does it stop being less than 0? Well, that's up here at 4. And we can't quite get to 4 because at 4 it's 0, so we want to be just short of 4, so like 3.99, so 4 but with a parenthesis. So there's the interval when f is less than 0. And the last one, when is g greater than f? So when is the y value of g greater than the y value of f? Where is g higher than f? So visually, how do you think about that? So here is where g is higher than f. So again, think about domain. I want to start on that left side of the graph. So the very left point. Again, I don't want to use the 5. That's going to keep going and keep being higher. But the x value there would be negative infinity. And then where does it stop being greater than f? Well, it stops just short of 1, because at 1 it's equal to f. So we want to be 1, but with a parenthesis. And of course, the infinity also gets a parenthesis. So that's how you look at a graph and think about these intervals where one particular function might be higher or equal to or lower than another function on the graph. I know that was an area that a lot of students struggled with in Algebra 2. It was one of the early units that we did, and I know all the Algebra 2 teachers talked about that as being a tough unit for the students. So hopefully it seems a little bit clearer now. Okay. So what I have here is a graph of some temperatures versus time during a day. And so we can see that the temperature is increasing. I just went from 0 hour all the way to 24 hours, so it's 24 hours of the day. So we see the temperature increases and then decreases as it gets into the night. So we look at a question like, when was the temperature over 73 degrees? All right. So what I've done here is I've got a line here where 73 degrees is, and so we'd say, when is this graph of the temperature over 73 degrees? And so we would see it's, this period here. This is all the time, right, where the graph is over 73 degrees. So what x values does that incorporate, right? So when was it over 73 degrees? Well, if it was 73 degrees at 8 o'clock, that means it wasn't over 73 degrees. Okay, but that was definitely the start of that period or that interval when the temperature was over 73 degrees. So since I can't quite reach 8, it's not exactly, it's going to get a parenthesis. And then since it does keep going on, just for argument's sake, let's pretend that the temperature at the end of the graph just stays flat forever so that we can use this idea that it's just going to stay above 73 degrees forever. Global warming, so we can use an infinity here. So at 8, it got to be 73 degrees, so then after 8, it was above 73 degrees, and then forever going on, it would be above 73. So from 8 until forever. What about when is the temperature 86 degrees or more? So again, what I've done here, I've got a line here showing when 86 degrees was. So when was that temperature 86 degrees or more? So you can see here at 12 o'clock, it hit 86 degrees. All right, and so it says 86 degrees or more, so that means we could include the 12 as part of our answer set. And then when did it stop being 86 degrees or more? So all the way from 12 on. And here, pretty much what would be 19, so 1900 hours, like 7 o'clock at night. That's about when it went below or hit 86 again. And again, hitting that point, it's at 86 degrees, right? So those get brackets. So there's an interval between two numbers where, so that kind of makes the context like when is one thing, when is one graph above another graph? Like how does that work as an interval? So maybe that helps a little bit more to have the context. All right, so here we're going to look at solving some inequalities and then writing our answers in interval notation. So this deals with the essential question today: how are we going to use interval notation when we solve? But we're just going to solve an inequality just like we solve an equation. There's just one major difference when solving an inequality and solving an equation. But so since I am solving, I want to think on the line, lines of undoing things and making sure everything's simplified first. We talked about on block day how to make a problem with fractions in it easier by using an LCD to get rid of those fractions. So I'm going to apply that same idea here. Seeing that the two denominators are 2 and 7, that the least common denominator would be 14. So I'm going to multiply every term by 14. So make sure it hits every term. So then as I look at this, the 14 and the 2 would reduce, and that would just leave me with a 7 that's going to multiply the 3x, and so that would give me 21x. And then on the next term, the 7 and the 14 would reduce. 14 divided by 7 is 2, so that's going to give me a 2 here to multiply by, so that would give me a positive 8x. And then it's greater than or equal to, and then on the last one here, the 14 doesn't have anything to cancel with, so it's just 14 times 5, which is 70, so it's going to be negative 70. So, sorry, negative 70. And then from there, it should be pretty easy to solve this. I want to get, combine my x terms here. So that'd be 21 or 29 x's is greater than or equal to negative 70. Divide both sides by 29. So x is greater than or equal to negative 70 29ths. So how do we write that solution in interval notation? Something we worked on, on the quiz and stuff. How do you take an inequality and write it in interval notation? So when I look at this, x is bigger than 70 29ths. That means this is the smallest thing. So that's going to go on the left of my interval notation. Small thing is on the left. And then since it's equal to, it's going to get a bracket. And then saying that every number bigger than that, so that means we're going to keep getting bigger forever. So there would be our solution set in interval notation. All right. Second problem is pretty similar. We got some more fractions. So look at those denominators and say, what's your LCD? So 5 and 2, of course, that would be, the LCD would be 10. So I'm going to multiply every term by 10. So here the 10 and the 5 reduce. Going to leave me with a 2. That 2 is going to need to distribute here and here, so that's going to be a 4x plus 3. Oops, plus 6. And then minus. All right, and then go to the next piece. So 10 and 2 would reduce, give you a 5, and that 5 will distribute in there. So 5 times 3x would be 15x, and then 5 times 1 would be negative 5. So here I need to be really careful, because I'm bringing multiple things down at once, not just like over here where I brought down just down 21x or just down 8x, because I'm bringing the 4x and the 6 down at the same time from the same thing. I really should put those in parentheses, like those pieces are grouped together. And the same reason I should have parentheses around the 15x minus 5. And why that's important is because this minus sign here basically needs to distribute through this. If I didn't put that in parentheses, I would definitely lose that idea. So it's a little thing which can make a big difference. We talked about with calculators how it's important to like group things. It's kind of the same thing. Like these pieces are all coming from the same place, so they should be grouped. So gotta really watch out for that. It's be tricky. So here with the 10 and the 2, reducing down to 5, and then distributing. So that's going to give me 20x plus 35. And again, I'm going to put that in parentheses. You know, in fact, it's not as important on this one because it's the only thing that's coming down. Like there's not more to do over here. So really these parentheses aren't going to matter. Where really the only set that does matter is this one here, because that's the only one that's got something in front of it that we need to worry about. You know, the purple set doesn't actually matter because the only thing in front of it is a positive 1, and distributing that, it's not going to change anything. So, so as I try to simplify this, so again, that purple set of parentheses really isn't doing anything, so just 4x plus 6. Now as I look at this next set, minus 15x, so minus 15x, and then minus negative 5, so that's going to be plus 5. So there really we see what the parentheses are for, is to change that second sign, and then less than, and then the orange parentheses aren't doing anything, so it's just 20x plus 35. I have some like terms here on the left, 14x, or 4x minus 15x, so that'd be negative 11x's. And then some constants here, so 6 plus 5 is 11, so plus 11. And I'm going to move all my x's to one side. So I'm going to add 11x to both sides. And then, since I'm moving everything to the right there, I'll move my numbers to the left, so minus 15. So that gives me negative 4 is less than 31x. And then divide both sides by 31. So I want the x to be on the left, so I'm going to move it over there. The negative 4 over 31 will be on the right now. So I need to pay attention to is that my sign here is opening up towards the x. So as I write it down here, I need to make sure it stays opening up towards the x. So since I flipped the equation around, I'm just going to make sure that sign flips around too. So I just like reading them this way. You don't have to do that. I find it easier to do when you do this though. So maybe a best practices idea. So as I go to interpret this and put it into interval notation, I want to look at that number. So x is greater than negative 4 over 31. So the negative 4 over 31 is small. So it's going to go on the left. It's not equal to, so it's just going to get a parenthesis. And then we're saying that x is every number bigger than this 4 over 31. So we're going to go to infinity. So there's our interval notation. All right, last one of these, and this will be the last example on this video, and then I'll make another video for the rest of the examples. Pretty similar problem. Right, we got a mixture of fractions and decimals here. You know, not a great thing. You know, we could turn them all into fractions. We could turn them all into decimals. I think most people would be happy if they're all decimals, especially since this is a nice fraction. It's not going to give us some crazy decimal answer. I think going into decimals is fine. If this was something really weird like 3/7 or something like that, I would not want to turn this into decimal because that would be something we'd have to round. So I then probably would turn this into a decimal fraction instead. But since we have a nice fraction, I'm going to go ahead and turn it into a decimal. We want to just have like some consistency here, so don't want fractions and decimals at the same time. So I'm going to go all decimal. So 0.75 x minus 0.2 x minus 6 less than or equal to 0. So like terms, 0.75 minus 0.2 would be 0.55 x minus 6. Oh, pretty easy there. So I'm going to kick this 6 over. So it gives me 0.55 x is greater, less than or equal to 6. And then we'll go ahead and divide by 0.55. So of course on the left we would just have x, and on the right we have 6 divided by 0.55. So if I go and look that up on the calculator, I don't get a nice decimal. It's going to be 10.9090 repeating. I don't really want to round this as part of my answer. So what I want to do with that, I'm going to get rid of that decimal in the denominator by multiplying it by 100, since it's in hundreds place. Again, something we talked about on block day, how to get rid of decimals. And so what I get with that is 600 over 55, which then I actually recognize as being reducible. So I can take 5 out of both of those, and there are 120 5s and 611 5s and 55. So where I end up with that is x is less than or equal to 120 over 11. So how do I write this in interval notation? So x is less than or equal to 120 over 11, so this means this is the biggest thing in there. So that means it will go on the right of the interval. And since it's equal to, it gets a bracket. And then we're saying x is every number smaller than that, so that means that's an infinity idea. But since we're talking about infinity smaller, it's going to be negative infinity. And of course, infinities always get parentheses. So there is our interval notation for that answer set. Again, this will be the last example in this video. You'll go to the next video on this within this playlist to see the other examples.